máximos o mínimos locales, y eso es lo que se trata de evitar, ¿no? Y en este caso se resuelve de esa forma. Vean, si ya tengo 5 generaciones, ya eliminé todos los outliers, los que están más afuera de la solución, y casi ya los estoy concentrando donde sí pueden ser las zonas más recomendadas, ¿no? O donde puede encontrarse la solución que estamos buscando. Y vean, después de 10 generaciones nada más, son 10 generaciones, ya están todas concentradas en el pico más alto, ¿no? Entonces, este es más o menos para mostrar qué tan rápido puede encontrar soluciones, ¿no? Y ya pues para complementar algunos híbridos, estos son neurofusis, son sistemas difusos que se entrenan como si fueran redes neuronales. Vean, aquí pues le estamos añadiendo capacidad de aprendizaje al modelo difuso. Y esto es, pues la red neuronal, las hacemos adaptativas. Una red adaptativa tiene que no nada más cambiamos los valores de las ligas, sino que es posible cambiar los valores o los parámetros de algunos nodos. Entonces eso lo hace mucho más adaptativa que las redes normales. Y con esto podemos formar sistemas de inferencia difusos cuya combinación hace lo que está como ANFIS, es Adaptive Neurofuzzy Inference System, que es uno de los modelos más populares porque aparte está implementado en MATLAB y se puede tomar casi para desarrollar ejemplos muy rápido, ¿no? Bueno, aquí no voy a detallar esto ya por tiempo, pero si ven ahí estoy tratando de obtener una solución y las funciones de membresía, lo que se hace es que, si ven hay nodos de color morado y unos nodos verdes, esos sí se pueden cambiar, los redondos no. Y en el primer paso, los nodos morados son los que tienen las funciones de membresía. Y los nodos verdes lo que tienen es parámetros para obtener una salida. Entonces, en el primer paso lo que se hace es se estiman esos parámetros de una función que me va a dar la salida final y hago una medición parecida a las redes, mido contra una salida deseada. Como voy a obtener un error, normalmente me echo para atrás y ajusto las funciones de membresía. Y a las funciones las empiezo a mover, las hago más anchas, muevo el centro, muevo de un lado u otro y las voy ajustando hasta que, el proceso me va a decir cómo van a ser los parámetros finales. Y vuelvo a hacer el mismo proceso y hacia adelante adapto los parámetros y hacia atrás adapto las funciones, ¿no? Entonces es en 2 pasos ese proceso. Y termino pues con funciones como las que están ahí, que inicialmente todas eran del mismo tamaño, ¿no? Y cada una de las ramas que tengo en la gráfica es una función, una regla if-then. Si X es A1, entonces me va a dar una salida, ¿no? Si X es A2, me va a dar otra salida. Y todo pues, entonces lo que estoy ajustando son redes neuronales, reglas de salida que al final, para obtener también ya la salida final, tengo que hacer una defusificación por medio de un promedio ponderado o centroide ponderado, ¿no? O hay otros métodos. Este es un ANFIS generado precisamente por MATLAB. Si ven ahí la cantidad de nodos que se tienen, aunque la entrada nada más son 2, pero cada uno tiene 7 propiedades lingüísticas y pues forma un ANFIS más complejo. Y ese lo utilizamos para el procesamiento de llanto de bebé, con el que hacemos la identificación de patologías en bebés de poco tiempo de nacido, ¿no? Los porcentajes que hemos logrado con pues han sido muy altos, aunque pues son modelos que probamos y luego los sustituimos por otros, ¿no? Pero cada uno genera una tesis al final. Esta es una red neuronal relacional difusa. Si ven, es una combinación, pues ahora también al revés. Ahora es una red neuronal que tiene valores difusos Y es una red nada más muy simple, una capa de entrada y una de salida, y las ligas son valores relacionales y se obtienen por medio de relaciones matemáticas. Y si ven aislada cada clase, más o menos se vería como la segunda gráfica, tiene una entrada y da una salida. La salida también es difusa y se tiene que hacer un cálculo para ver a cuál clase es la que pertenece. Y con lo que se calcula es nada más con esto, si ven son productos relacionales, este es el producto max-min, que también se conoce como producto circlet, y eso es todo lo que se hace para calcular la salida de la red, no hay más, ¿no? El aprendizaje sí es un poco similar a la retropropagación, pero lo único que tengo que hacer es tomar el vector de entrada, que son los datos de entrada que tengo, y lo paso por la matriz que se quedaron con los valores relacionales, y ese es todo el trabajo de la red, ¿no? Ahora, este mismo tipo de red, para adaptarle los parámetros que necesita, lo hicimos a través de algoritmos genéticos. Y si ven, pues, el vector, aquí está de forma vertical, pero cada parte refleja un parámetro, lo paso por la función, la Fuzzy Relational Neural Network, hago una serie de operaciones genéticas, obtengo al final cuál fue el conjunto de parámetros que me está dando el mejor modelo de la red, y ese es el que me dio los mejores resultados. Y de esta forma, pues, yo no tengo que estar pensando qué valor le pongo, sino que iterativamente se lo dejo al algoritmo genético, ¿no? Este es otro método de granulación difusa, y este es para reducir vectores de características muy grandes. Este se está utilizando para reducir vectores de electroencefalogramas, sobre todo estamos identificando estrés y viendo qué efecto puede tener la música en la reducción de ese estrés. Entonces, para no manejar vectores demasiado grandes, lo que usamos es lo que se conoce como agrupamiento difuso o granulación difusa, y el vector completo, si ven, al final nada más lo vamos a medir en cantidades de low, mid y alto, bajo, medio y alto, a partir de lo que es la segmentación de la señal. Y se utilizan diferentes funciones de membresía. Si ven, pues, en el tercer nivel tenemos una serie de funciones, no están muy bien definidas, pero tenemos triangulares, trapezoidales, otra creo que es tipo pi, y usamos un operador max-min como el anterior que mostré. Y esa es la entrada para una red convolucional, que aquí se hacen ya las operaciones clásicas de una red de este tipo, pero teniendo como entrada nada más los datos de los gránulos, no de los vectores completos, lo cual redujo muchísimo las dimensiones del vector, ¿no? Y al final, pues, obtenemos la salida que también es difusa. Nos dice si hay estrés y en qué grado, ¿no? Bueno, aquí nada más es mostrar cómo los algoritmos genéticos también pueden ser usados para optimizar redes. Normalmente una red neuronal está totalmente conectada, pero muchas de las conexiones no sirven, o sea, no se mueven nunca. Por lo cual, pues mejor tratamos de dejar nada más las redes, las conexiones que sí sirven o que son relevantes a través de algoritmos genéticos, y se hace pues esta matriz de conectividad que se está reflejada, si ven en la parte de abajo está el vector completo que representa la red. Y ese es un individuo que lo vamos a evolucionar hasta ver cuáles son las ligas que sí dejamos y cuáles no, ¿no? Bueno, este es otro caso de cómo se pueden generar reglas y luego difusas, y luego ya después de las reglas difusas, cuáles dejamos, porque si ven en el primer caso tenemos duplicadas 2, y después a través de la evolución ya eliminamos una. Pero también, si pueden ver, las funciones de membresía primeras están todas uniformemente distribuidas, y ya en la parte de abajo ya se movieron y ya se adaptaron a través también del algoritmo genético. Entonces es una forma también de utilizarlo con este fin, ¿no? Y pues finalmente, pues aquí es un modelo completo utilizado en una empresa, creo que química, en donde todas las operaciones las controlan por medio de modelos de inteligencia computacional. Si ven, desde la entrada es difusa, luego hay una red neuronal que tiene una salida difusa y luego tiene un control que normalmente también a través de operaciones genéticas se optimiza, pero una vez que ya está viendo el funcionamiento de la planta y regresa, actualiza parámetros y vuelve a dar la retroalimentación y lo mantiene en operación ahí constante mientras se mantenga la operación tal y como se está planeada, ¿no? Bueno, y ya eso es todo. Y pues, en homenaje a Sadegh, él fue el inventor de la lógica difusa. Y bueno, le identifiqué para que no se vayan a confundir quién es quién, ¿no? Desafortunadamente ya murió el profesor Sadegh, pero dejó ese legado que es la lógica difusa y todas sus aplicaciones. Pues muchas gracias y creo que no va a haber preguntas, así que por ahí me pueden encontrar y si tienen alguna duda, con gusto, ¿no? Se las puedo contestar. Gracias.
Tal vez hay dos preguntitas breves, difusas. Por allá hay una. No sé si le llevan porfa el micrófono a la muchacha que está en medio, en la línea G, tal vez. Ahí va el micrófono.
Mi pregunta es que en una de las gráficas donde salía la temperatura y la tensión, digamos, era como un diagrama triangular, ¿por qué se asignaba que la tensión era nada cuando en realidad eran como 10 voltios?
Bueno, es un nada difuso, o sea, va llegando gradualmente al cero, pero va parando, no es drástico, ¿no? Un sistema de control difuso normalmente no se apaga, se mantiene en el punto ideal para que no haya el apagado, encendido, que…
Okay.
Entonces sí hay, es nada, pero llega gradualmente al nada. Si realmente ya está calientísimo, entonces sí apaga, ¿no?
Entonces sería como un sistema de control que tal vez está a esa tensión funcionando, pero para que se llegue a controlar la temperatura.
Sí, correcto.
Okay. Muchas gracias.
Una última pregunta. Si no, cualquier cosa, Carlos va a estar por acá y podemos conversar con él al final también. Muchísimas gracias de nuevo, Carlos. Un aplauso.
Muchas gracias a Carlos por la excelente presentación y también por atendernos allá en México cuando estuvimos. Fue una experiencia nos llenó muchísimo de muchas cosas. México está muy bien en investigación y les tenemos de esa buena envidia definitivamente y esperamos volver definitivamente. Muy bien, mi nombre es Federico Ruiz. Buenos días a todas y todos. Yo voy a presentar a Michael Beetz, que es la siguiente presentación. Michael Beetz es profesor en Ciencias de la Computación en la Facultad de Matemática e Informática de la Universidad de Bremen. Él es actualmente el director del Instituto de Inteligencia Artificial de dicha universidad. Michael recibió su diploma en Ciencias de Computación con distinción en la Universidad de Kaiserslautern. Sus grados de maestría y doctorado los obtuvo en Ciencias de la Computación en Yale y su habilitación como profesor la obtuvo en la Universidad de Bonn en el año 2000. Bueno, él ha participado de una gran cantidad de proyectos, voy a mencionar algunos, por ejemplo, en algún momento fue subdirector del proyecto de excelencia, clúster de excelencia alemán, COTESIS, que justamente Francisco y yo fuimos parte de ese proyecto también en ese momento. Posteriormente a eso, Michael ha sido miembro del comité directivo de la Red de Excelencia Europea en Planning, en planificación con inteligencia artificial, PLANET, en particular el coordinador en el área de investigación de planificación con robots. Michael es editor asociado a la revista Inteligencia Artificial y coordinador del Centro de Investigación Colaborativa alemán IS, Everyday Activity Science and Engineering, desde 2017 hasta la fecha. En el 2021, Michael recibió un premio junto con su grupo, con el mejor proyecto académico en la Fundación EHI, por la relevancia en el trabajo realizado del grupo de Michael en industria y comercio para tiendas de minoreo, en la aplicación de sus técnicas en ese tipo de ambientes. Y recientemente Michael recibió el premio de financiamiento avanzado Advanced Grant del Consejo de Investigación Europeo. Dicho premio es otorgado a científicos de punta trabajando en áreas de alta innovación, en el caso particular de Michael por sus contribuciones en la creación de robots con capacidades de planificación de acciones predictivas. Sus principales áreas de investigación son control basado en planes para agentes robóticos, procesamiento y representación de conocimiento para robots, aprendizaje integrado para robots y percepción cognitiva. Sin más, le voy a dar la palabra a Michael. Thank you, Michael, to be here, and please come and give us this great talk that we have been working and waiting for you.
So, good morning, everybody. Thanks a lot for having me here, and I think it was a plan for a long, long time, and I think you probably don't know, but we have a very, very fruitful cooperation with Costa Rica, right? So when I was back in Munich, I think the first one was Alexis Maldonado, and he was coming from a DID stipend and joining our group, and I was completely impressed by him. So for one thing, kind of the technical skills he had, and the other things were how good a teammate he was and how he helped everybody and simply made the team better, right? And at that point I said, well, Alexis, are there more Costa Ricans, and can we get one? Can we get some in our lab? And Alexis recommended his friends Federico and Francisco. So we got them in, and they did the doctoral degree in there. And I think it's just amazing to see these people growing up and having their careers. And
Sorry for the interruption. I want to help you because
Okay.
this is not well placed.
I see. Oh, okay.
Now you can move around a little bit.
Is that better?
Yeah, it's on. So
yeah,
you can
it's
stay
okay.
here or you can just move around. Sorry.
Okay, cool. Yeah, and I think you also, the guys become big friends, and you get used to them. And I think some of you who know Federico well might be surprised that we had most of the time our scientific discussions around 7:30. And so that's kind of very early, but it was the case because Federico was working through the night. And Francisco, I think he was there. He got married, and he got a son also in Germany, and he's, I guess, now 1.90 meters tall, and yeah, it's kind of impressive. And I think we kept contact all the time. And we are trying to do things together, and I was always looking forward to coming here. I would also like to thank the speaker before me for giving such a comprehensive introduction on the techniques of artificial intelligence and how you can solve all these kind of problems we have with the different techniques. So that's kind of an excellent background, and that frees me a little bit to talk about kind of some other aspects of intelligence. So the aspect that I want to start with is kind of going one step back and asking a very fundamental question, right? And that question is, why do we as humans and some animals have intelligence, right? And the reason is very obvious, right? The reason is we have intelligence because we have to act successfully in the physical and the social world, right? And all the kind of species that have not managed to actually act successfully in the world, kind of they are dead and they are extinct. And so the very purpose of intelligence is acting successfully in the world, right? And it's important that we keep that in mind, because kind of this tells us whether we are actually successful with understanding intelligence or not. And if we don't manage to actually realize systems that act successfully in the physical world and the social world, then we are not successful, right? So if you buy that, right, and I think there are very good reasons for that, kind of the fundamental computational task that every intelligent agent has to solve is that, given some underdetermined task requests, it has to find a body motion that achieves the desired effects and avoids unwanted side effects, right? So if you are a robot or a human, right, the only thing you can do is actually move your muscles, move your body, and even if you think about language, right, it's actually moving your tongue in your mouth in order to communicate, right? So if we don't understand kind of how we actually generate the motions that have the desired effects and avoid unwanted side effects, then we have not understood intelligence, right? And intelligence is even more than that, right? So intelligence is not just acting successfully. In particular for human, it's about understanding what we are doing, right? Understanding the consequences of our action and understanding what somebody else wants us to do, right? So I'm married for more than 30 years, right? And even after that time, my wife and me need to occasionally negotiate what it means to clean up the kitchen or something like that, right? And to actually do a task as it's expected by somebody else requires a huge level of intelligence. So, again, if you buy that, right, so then if we study artificial intelligence, we should actually study artificial intelligence by building robots, right? Because robots are actually agents that can act in the world, and if we program to act successfully, we probably learn a lot about intelligence, right? So if we are looking at that, so a robot has an articulated robot body, right? So it has a kind of the links, it has the joints, it has motors at the joints, and the only thing the control system can do is actually moving the joints of the moving the motors of the joints, right? And so that means the control program is creating a body motion, right? And that body motion is acting in the world, so it has physical effects. And if we are talking about the tasks that the robot control system should achieve, then it's almost all the time something kind of a goal state or kind of a stretch of goal state in the environment. So that brings us to the purpose of the robot control program. So given an underdetermined task request, and examples are set the table, clean up, bring me something to drink, generate a body motion that achieves the desired effects and avoids unwanted side effects. Okay. So if we take an example, set the table. Can we have the video? It's underneath the image, yeah. And so here you see what it requires from a robot control program to actually execute a task like set the table. So you have a mobile manipulation robot with 2 arms that can navigate in the kitchen environment. And it's opening drawers, it's opening doors, it's picking up objects and placing them where they should be placed. And you see on the lower right, kind of a little bit visualized the reasoning that goes on in that robot control program in order to perform the task, right? That program is completely autonomous in the sense that it perceives the objects that it has to manipulate and that it's doing reasoning. So, for instance, you don't want to have your robot bringing dirty cups to the table, or kind of placing them the items in the wrong arrangement. So it's kind of a very deep reasoning task that requires lots of knowledge and reasoning through many aspects, like spatial reasoning, prediction, kind of seeing the effects of action, foreseeing them in order to avoid problems, or kind of picking up an object that allows you to avoid regrasping when you're putting down. So then you have to imagine how you will put it down in order to do that. And you see the same robot control program, then cleaning up. So suddenly things are thrown away and not placed. You kind of have to reason about which objects you have to throw away, and so on. And building such robot control systems is an extremely complicated enterprise, and it requires a big team where everybody is actually not only doing their job, but also integrating with the others and making things work together. Okay, so if we are seeing that, right? So, and we see that very complex body motion that the robot has generated in order to set and clean the table. And we subtract the task request from that, so something like set the table, clean the table, bring me something to drink. So the difference between both of these things has to be in the knowledge and the reasoning of the robot control system, right? And there cannot be another place where it is. And I think it's kind of our job as researchers in intelligent robotics to understand how kind of software systems of this complexity could possibly work. And that's kind of one of the big challenges in science, as it's actually some of the intermediate steps to understanding how the human brain works. So, if we are taking a little bit more an engineering perspective, right? So as engineers, we have the problem that we have to write robot control programs for many different robots, for many different tasks, in many different environments, right? And if we do that as proper engineers, right, we have to think about how can we program the system in a generalized manner so that actually when we find out a solution of doing something, that it can be transferred to other robots, to other tasks, to other environments, right? And this is kind of very complicated. And if you're looking at that, So I said that the capabilities and the complexity of the control program of the robot depends on, so it's not a function, but it's kind of a dependence on the robot agent, right? And robot agent can be one with very limited physical capabilities, can be one that has kind of cameras for vision, can be one that has multiple hands, arms. But I think the distinctions that are very important is whether that robot agent actually also has to act with other agents. And the most important other agent that we have in robotics is the human, right? So if we are looking into the future, if we are looking at our aging societies, we have to have robot control systems that act successfully together with humans and do what humans want them to do. So if we are taking that complexity dimension at the right, so you have at the simple complexity side things like vacuum cleaners, right? So one robot actually exploring an environment, kind of taking random paths through the environment. You have things like autonomous vehicles that do point-to-point navigation, factory robots that do complex manipulation tasks, but the whole environment is actually built so that their motions are working. And then you have robots like the ones we have seen, so robots that kind of do pick and place tasks, meal preparation tasks, kind of you can even think of robots learning to accomplish manipulation tasks by reading instructions in the World Wide Web and by watching videos, instruction videos in websites like WikiHow and actually translate that into control programs so that they can achieve their task. And again, the most complex things is when we get the humans running together with the when we get the robots running together with the humans. So if you take basically the same complexity route, and now we look how nature has actually solved that, and what were the major steps that we found in nature to go that pathway. And you see kind of at the left side, animals that have motion skills and very distinct and very few motion skills, like a frog that jumps away if a bird is coming, or jumps away when jumps onto the fly when it's coming. It's getting more complex. But if you see the evolution of the capability, there's one step which is really a huge step change in the capability of intelligence. And this is actually when systems accomplish goal-directed object manipulation tasks, right? If you're looking at the cognitive science and kind of biology literature, at that point where you have goal-directed object manipulation, you see many cognitive capabilities kind of developing in very short time periods. So, and these capabilities are using a tool. Using a tool is, from a perspective of a robot control program, kind of a huge thing, right? Because you change your body. You cannot kind of just simply learn with your body to do tasks, but if you are kind of taking a hammer in your hand, you have a different body. If you take a knife in your hand, you have a different body, and you can do other things. And the question is, how can we actually do that if we just get a task request, we reprogram ourselves to use different tools to do the tasks more competently? The other thing, so we see the joint co-development of language and action, right? So actually, language is not something that is actually developed in the abstract, but language is a means for acting successfully and communicating, right? And this is a reason that you communicate what you think that others do not know and what others need so that they act successfully. And you have things like the simulation theory of cognition, right? So that you can actually run a prediction of your robot control program in your head and reason about how that it will probably go before you're executing it, right? So that makes you into a robot control system that is very foresightful. And yeah, we already heard, right? So we are now in an age where kind of the development of technologies is just amazing, right? And we see a tsunami of technology advancement in the area of deep learning, right? And I think the new things we see is that we can have machine learning that takes in all the text in the web, right? And they can do things like do a probabilistic text completion based on that you have read everything that you can read in the web, right? And this technology is just amazing, right? And it's not just in language, it's also in the domain of images, right? So where you can say, look at all the images in the web and all the descriptions of the images in the web, and then kind of see what you can learn out of that, right? And it's vision, speech, text, and now they start to actually combine that with action, right? And the reason we can combine it with action and that we might get sufficiently large data sets is kind of the jump in technology in simulation engines, right? So we, in particular, in game engines, we see that we can represent environments at a level of detail which we have never seen before, right? And you can have a photorealistic model of your complete apartment, and your Unreal Engine will update that model in real time, right? And it can also, it can render that, and it can use that model in order to do a simulation of that robot control program, right? And so what some of the researchers actually see is that if we are getting these things together, and then we might make another jump in AI system capability, right? And I think this is where a substantial fraction of the research and technology community currently is, right? And yeah, example, the robotic transformer. But we also see surprising failures of that technology, right? So here you see, if you prompt a system like a generative AI system that generates images, and you say, you want a salmon swimming upstream in a river, I think you got at least at some point these images, right? And it's amazing how cool these images are, right? So they are fish, right? They make swimming motions. They have placed them in a reasonable way in a river, but they used cooked salmons, right? And the reason is, if you are just looking into the web and you get the statistics of images, most of the pictures of salmons are cooked salmons because of the recipes, right? And kind of here's another example. So ChatGPT at some point, you can ask, did you know that there is no country in Africa with a K? And ChatGPT gives a very interesting answer. While there are 54 recognized countries in Africa, none of them begin with a K. The closest is Kenya, which starts with a K sound, but it's actually kind of spelled with a K sound. It's always interesting. So again, it's kind of very interesting, right? So if you look at the system as a probabilistic text completion system, that answer makes complete sense, right? So and it's just kind of misguided by the prompt we set, because we actually assert with the did you know that there is no kind of country in Africa starting with a K. But the answer it suggests is it's saying yes, but it actually gives examples which are counter-examples, right? So it doesn't understand kind of the logic of what it's giving, right? And the third one and last one, if we are looking more into robotics, also an interesting and old example. So you're having a small dinner party. You want to serve dinner in the living room. The dining room table is wider than the doorway. So to get it into the living room, you will have to remove the door. You have a table saw, so you cut the door in half and remove the top half, right? And again, if you see it as a statistic, text completion, it's absolutely fine, right? If you imagine the action that is actually described here, and you see it in front of your mental eye, right? So it's, you certainly don't want a robot that is getting his instructions from ChatGPT. And the causes of these flaws, so let me first make kind of one point. So one point is that this technology is simply amazing. And it's kind of a puzzle piece that we need to put into our artificial intelligence systems to really scale them to the real world. But the claims of researchers that actually claim that these systems are sufficient is bogus, right? And the reason is a fundamental one, right? That they have actually very clear limitations, and these limitations are due to the nature of the technology. So we've already talked about kind of that they create statistics, right? And creating statistics is a cool thing, because if you get sample points, you can interpolate between them. So you can actually make your kind of application domain dense through these technologies. Kind of another very kind of fundamental drawback is that these systems do not use models, right? So kind of if we as humans perform actions, in particular new ones, we typically imagine how we do the action, and we kind of mentally simulate them. We see these actions in front of our mind's eye, and we evaluate whether actually the action we intend to do will be successful, or whether there will be kind of side effects, right? And if we are doing that, that's another part of having a model, kind of, if your model is good and represents the structure of your problem, right, those diagnostic information, they also tell you how to change your program, and you can do that in a single reasoning step. And so that's kind of much more powerful, right? But it's also much more complicated, right? So the reason that kind of systems like ChatGPT can actually build kind of quasi-knowledge bases, I will come back to that, over such huge domains, right, is that they don't do models, right? So that they kind of just use the statistics, that they should use all the examples, and they solve optimization problems. And so that's a good thing for them, and without they can, but that means it cannot be the only kind of method that is going on there. And a third reason, and there are more of that, is that if we are looking at what a large language model is, it's not a knowledge base, right? A knowledge base is something where you have entities and you have relations between these entities, and you can talk about them and you can access them, right? In these large language models, the model is distributed in the weights of a system, and it's in a way represented that doesn't reflect the nature of the problem, and therefore we have so much problems kind of in dealing with these issues. And of course there are, as you can imagine, the whole field is doing all kinds of patches in order to solve that, right? So instead of kind of suggesting one action and kind of for a single task, you kind of put all kinds of queries about the actions you intend, and then you train it so that it basically satisfies multiple answers, so that you kind of avoid over-specialization, right? Another thing is, if you are kind of interpolating solutions and you make up solutions, you can still go and retrieve a web page and see whether you find a web page where this is actually sufficiently closely described, right? So that gives you at least some evidence of where you got the knowledge from and whether it's reliable or not. You can think about combining the technology using neurosymbolic, and as I said, so there's kind of multiple ways to deal with that. Oh, yeah. So let's again take our best teacher that we have, and this is nature, right? So, and can we have the video, Israel, please? Yeah, so here you see a boy, right? So it's in the pre-language stage, and it certainly doesn't have kind of all the concepts that you need to successfully execute the actions, right? But you see that the aim is of the boy to act successfully, right? So it dynamically, he finds out that it can use a glass for stabilization. Even though it's very shaky, it knows that it has to avoid that the kind of bowl has to tip over and so on, right? So this is, the boy has a lot of intuition of how to act successfully even before he can do that. So kind of there are many, so some of the researchers say if we are looking at the current stage of AI, we have to look at that stage of AI with a combination of humility and optimism, right? So, and humility because we have to actually appreciate how complex kind of intelligence is to model as a computational system, and that it is the orchestration of a substantial ensemble of very powerful cognitive mechanisms, right? So we have things like memory systems, episodic memories, semantic memories. We have things like simulation. We can imagine the images we see when we enter into a new scene. We can plan, we can make predictions and everything else, right? And we have no clue how a computational system has to be designed that can bring all these kinds of things together. And I think this is what we have to do hard work on. So I think one of the key things in my perspective, and that's kind of certainly very biased, is that one of these things is future action models, right? So that in our brain, we have representations of models of intended tasks and actions, right? And the computational challenge in having that is that we have to construct something that doesn't exist yet, right? But we have to construct it that it's actually very feasible and it has a very high chance of doing the right thing. And then we have to completely reason about that from all sides in order to do that, right? So yeah, so we have systems that generate solutions, but those systems do not understand the solutions, and they can't kind of do, and here you see that mental models of intended actions as probably one of the key things that we have to understand. And understanding for an artificial intelligence system means that we kind of need a whole lot of capabilities, including, I have to read that, knowing what is the knowledge about the domain, understanding how things work, being able to improve something to make it better, being able to evaluate, right? So the system has to look at the things and see whether it's good enough, analyze it, so to find the flaws and create kind of to debug them, right? And that's kind of something kind of that is known for a long time, right? So if you have, if an organism carries a small-scale model of the external reality and of its own possible action within its head, it is able to try out various alternatives, conclude which is the best of them, react to the future situations before they arise, utilize the knowledge of the past in dealing with kind of present and the future, and in every way react in a much fuller, safer, and more competent manner to the emergency we face, right? So if you see at the state of these deep learning systems, right? So it's clear that something like this capability is missing and that we need to see how we can get these capabilities into the systems, right? And just I think I have to kind of take one step before. And this is also clear, or it's not clear, but some of the researchers in decision-making, cognitive psychology, they have these models, right? So they say that intelligent thinking and problem solving is a two-system process, right? Kind of the two systems. One is thinking fast, so it basically takes things that it has learned, and this works extremely well in habitual situations. And there is a system 2, which is actually reasoning, full-fledged reasoning and thinking about all the consequences of actions, right? And if we want to have the next generation of AI systems that actually understand what they are doing and the consequence of their action, it's my perspective that we have to go towards a two-system approach to intelligence. Okay, so I'm talking a little bit about our own research and what are the big projects, and they are all related essentially to these ideas. So we have a collaborative research center, EASE, which investigates everyday activities, science and engineering. Our challenge is to have robots that accomplish things like setting the table, cleaning the table, very simple meal preparation tasks over a lifetime, right? And that they learn from their previous experience and get better in that. Have another project, which is an ERC grant, which kind of looks at the core. And the core is the future action models and how to represent them and how to reason with them. That's FAME. And we are currently have submitted a pre-proposal for an excellence cluster in the German Excellence Initiative, which is on co-constructing understanding and skills between humans and robots. And it actually kind of investigates how these systems actually can accomplish tasks for humans the way humans want them and negotiate them in order to do that. And in this project, also University of Costa Rica is kind of listed as a cooperation partner, so it's kind of a wide shot, but if we are successful, I think that's an opportunity to work kind of together. Right, so we have seen the robots kind of acting, so we have seen that part, but the important part here is how we generalize that, right? So we have the identical program running on different robots. We run it on different robots in different environments and even for different tasks. It is possible because these are pick-and-place tasks, right? And the thing is, if we are able to actually find a computational theory of pick-and-place tasks, we can probably kind of automate or help to automate kind of a lot of tasks, right? And because these are designed programs, they would also in some way overcome some of the problems of systems that are completely learned. So can we have the video in the upper right? Yeah. So here's kind of the question that the robot answers when doing that. Oh, so it should be endless loop, yeah. So you see the question that it's asking. So where's the milk box? It's on the shelf. It's in the cupboard, and the cupboard has a handle, and I have to grasp the handle, and I have to kind of move my hand according to the articulation model of that door, right? And the reason it's actually inferring these pieces of information is that it's so general, right? So that it can open all the drawers, all the doors, if it's kind of a fridge with vacuum, kind of, and other things. And that's kind of the game we are trying to play. FAME. So FAME is essentially kind of the idea, can robots build models of future actions they have never done before. And in a nutshell, what we want to do is we want to build kind of a simulation theory of cognition, so the robot should mentally simulate it. We can do that if we build the reasoning engines of robots on top of game engines that have these basic functionalities and basically access the main data structure of these game engines, which is called the scene graph data structure, and we represent them explicit as knowledge base, right? So if you look at the scene graph of the kitchen environment, you find something like you have the fridge. The fridge has components, which is kind of the container, which is the door, which has handles, and stuff like that. And you can go through the scene graph, through the data structure, subtask, and extract the relations about the kind of physical system that you're modeling, right? And this is actually a kind of a promising way to build lightweight knowledge bases. And in particular, if we can do that automatically from scene graphs, right? So then we could use all environments from metaverse and convert them into knowledge base, right? But because they kind of are based on a model of the structure, right? They don't have these kinds of problems that large language models have when they interpolate between things, right? Because the structure of how the world is actually composed prevents them from constructing, I don't know, a door that has a handle left but opens to the top or something like that, or anything like that. Okay, and can we have the video? So the kind of the challenge scenario is that we want to have robots that watch instructions in the web. Can go a little bit further. Okay, it shows the interesting stuff in a second. We are watching kind of the videos in the web, and we see people kind of doing these meal preparation tasks. We are using kind of technology that is used in deep learning, but what we are constructing is actually avatars in the virtual environments, right? And again, that forces us that we have models, right? And so when the robot is now watching a video in the World Wide Web, it's trying to kind of replicate the activity. So we are just starting on that, so that we don't have any anything that is seriously working on that. But the idea is that you mentally want to simulate what you are seeing in the video in your simulation engine, right? And with your own robot control program. If you're managing that, right, so then you connect what you're seeing with your own experience, with your own knowledge, with your own understanding of the knowledge, of how the world works. And this is important because if you're watching a video, you cannot observe the concrete physics in the environment. So when you're pouring, you don't know the viscosity of the fluid or other physical parameters, and you want to translate that to another body, which is a robot body, and you want to kind of execute it on other objects that you also do not know. And so that forces you that you understand the essence of an activity that you are seeing from the web just from observation and mentally simulating that. So that's kind of what FAME is about. And yeah, and you see some of the kind of the the tracking of the human motion and the adaptation is, I think, very good, but it's not yet generated from robot control systems here. Let's see. Oh no, can we get to the next slide? Okay, we had that. Yeah, so that's only background. The third big project, so that's kind of the pre-proposal where you also cooperation partner, is kind of you have robots and human doing things together, right? And if you set the table for together with the human and the robot typically have different understandings, different interpretations of the task, right? And if we want to have robots that do what humans want them to do, I think they have to kind of extract information from the task interpretation from the human that differs from its own task interpretation and construct a shared task interpretation and then construct a robot control program for the shared task interpretation, right? And so this is kind of a very large-scale interdisciplinary program, and where we have kind of researchers from many different disciplines that work together for this next generation of AI systems. Okay, and key things which are, again, heavy on the capabilities of AI systems are the ability of taking advice, right? So if you are a robot, right, and you are working in a kitchen, right, and somebody tells you, be careful, the water is hot. You have to make sense out of that piece of information. You have to understand where that actually interferes with what you are doing and how you have to change your course of action in order to implement the advice in your own actions, right? So, and these are the kinds of mechanisms we want to realize, right? Those things are far beyond what actually single research institutes or everybody else can do. So if you tackle these grand challenges that we have in our research agenda, you have to go for an open research approach, right? So you have to actually find ways to get researchers from other places with different perspectives into the game, trying their own thing, sharing their ideas, and also kind of having convergent research so that across the disciplines, so from cognitive psychology to robotics, you have to have a shared conceptual framework, shared concept that are agreed upon in the different disciplines, right? And you have to realize that together in order to make proper progress, right? And the only place where we in robotics have seen actually such a strong community to develop is the ROS community, right? And the ROS is an open software library where everybody in robotics can contribute, everybody can use parts of the software library and do their own things with it, right? And so that's also my personal view on that. So why was it that actually ROS was successful and so many other initiatives that were also trying to get open research were not, right? And I think we can see that. So the idea of the founders of the ROS initiative, right? They were actually building a complete manipulation robot at the bottom, and they were developing it with a complete control set, kind of control system for pick and place tasks, right? And they did it in a way that you simply could use their code, but they didn't try to standardize, right? They didn't force people to actually take standards, but everybody could do with that what they want, right? But what de facto is happening, right? So there are many very kind of components that are very resource intensive to develop, right? And which are not kind of research activities on their own, right? And you want to be a parasite and using these kind of things that already exist, right? And that actually motivates people to standardize, to actually look whether they can find ways to define data structures so that they can exchange them, that basically the processes they have come with APIs, and you can look at the APIs on how to use the code of somebody else, and you trust the community that they are actually building kind of orchestrations of these modules that work and bring the field together, right? And I think this initiative was so successful that I think by today, about half of the professional robots are using some components of the ROS software infrastructure, right? Okay, so this is kind of at least what I have taken as a lesson from why ROS is actually working and other systems not. And so then the question is, how can we actually realize that again? And so our idea is that we want to build kind of also complete robot control systems with their environments, with their tasks, and we want to implement them as digital twins, right? And those environments, they should run in the cloud or be downloadable without actually the people using them having to do installation work, right? So they just kind of are usable as if they were games, right? And yeah, can we have the video? So we put in a lot of effort where we actually model our environment, right? And in a very photorealistic way. So we model it as a scene graph. I've said earlier that when we have a scene graph, it's also a lightweight knowledge base that the robot can use. And yeah, and so we actually want to share that environment together with our robots, with the community to work. And it's not only that you have these models, but they must actually work. Doors must open, there must be kind of contents. You have tools, you have objects that change over time. And again, so building these environments is a community effort, right? So if some of the researchers actually construct a kind of, can we stop here just a second? Yeah, so this actually has shown before that even though that is a scene graph, the whole environment can be generated from a symbolic knowledge base. Kind of, this is a lightweight knowledge base. If you have the detailed geometric models of the components, right? So whenever you see essentially a game environment, it's a knowledge base, and you can ask questions about it, right? So you can say something like, find all entities that are a subclass of the class handle and highlight them in green, right? And your system will simply show them, right? So that's actually kind of an indication that your system has a deeper understanding of what it's actually working on, right? And we can continue, yeah. And you see more examples of these questions, right? Yeah, so it's more like a Siri agent that you can ask any question and you can kind of work on it. And it's a knowledge base, right? So you can actually load it in our open knowledge service. You can click on items to highlight them. You get to the symbolic names. You get knowledge about the items that correspond to Wikipedia entries, or kind of some information of Wikipedia entries. And you build that for different kinds of environment, right? And the key idea is what will happen if we, as a kind of robotics community working on intelligent robots, build together such infrastructures and actually kind of bring them together in virtual research buildings in the cloud, right? So we would want to have research laboratories coming from very different research groups. They are brought into that virtual research building. So for instance, so this is an example from the European Network of Excellence Centers in Robotics. So in this case, if the partners kind of play the game, right? So you would have a research building where you have our robot doing the table setting. You would have the robots of Tamim Asfour also doing kitchen work. You will have some of the most advanced robots for physical human-robot interaction from DLR. And you would hope that everybody in that European network is contributing to that. And yes, so Israel, this is your try, yeah. So this is actually now that system. So we are currently building that. It's not working properly yet, but you see that you can go into household work for robots. You could basically select at least 2 different robots, 2 different environments, and you can simply run the system into a Docker environment, right? So that means if you are in your research group and you kind of want, you are in a European project, and you might develop a dialogue system for robots, right? But by, we are kind of trying it with a weak internet connection. But here you see it. So here you get the environment and the robot that you are selected. So you can go to the left and click on the first instruction, as it's kind of typical for Jupyter notebooks. So you have to click on the one, yeah. And now you have to click on the arrow, and now it's actually bringing up the kind of the system, right? And it's important because it's coming up for, say, students in Africa that don't have such robots, that don't have such environments, right? But it gives researchers somewhere in the world the opportunity to actually join leading-edge research efforts and actually place themselves in that community, right, to work together with the other researchers and do something together, right? And you see it's an identical program that actually runs on our robots, right? And this is the way we want to make that accessible, right? So what we are currently trying, we are trying to get all our different project results as these kinds of Docker environments. So if you download it and you run the Docker environment on your own PC, you could probably even kind of run it with Unreal rendering and simulation, so the kind of the photorealistic mode. And yeah, and we will want to see how that is going. And yet it's also kind of a means for doing replicable research, right? So what you want to do is you want to have your research program, and instead of having a table with your experimental results, you're actually storing kind of an experiment in that setting, right? So that means researchers who want to understand what you have done in the paper, they can actually actively analyze kind of the experiments, the program, they can play around with it, and we hope that that would be a great push for doing research more successfully and having faster progress in the field, because we can build on the results of others, right? And we can combine them, and that should actually give us a huge push, yeah. Israel, can you stop it? And or you can simply delete the web page, the kind of the tab. Yeah. Okay, so now there's another button right next to it. It's kind of sorry. We have to go onto the page again. You have to click on the, no, we are. Yeah, experimental data is the one that I want to see. So now, right, so you have run an experiment with a robot in an environment, right? So now, kind of the experimental data of that experiment, that is, these are accessible, right? So, and you can access them in an open knowledge web service, which is called OpenEase. And you can download essentially recordings of the experiments and kind of work with them as knowledge bases, which would also mean that if you are doing something like data-intensive machine learning, you can take all the recorded data and generate kind of special purpose data sets on that. I think I will probably show it on Friday when we have a kind of more Thursday. Okay, so then, yeah, let's leave that. You can go. And then we have another thing where you have access to the source code, right? So you can get basically all the source code of that. And you don't need to that. Oh, it's not found. Okay, yeah, we are building up the system. Can you go back? Yeah. And just as a second example, so we have food cutting robots. So if you click on the blue button, sorry, no. Can you go back? The green one, so I meant, yeah. So this is kind of another research project, and this research project is about building knowledge graphs, which are lightweight knowledge sources that you can construct from instruction websites like WikiHow, and you create a kind of a huge knowledge graph, as in the case of Google, right? But the purpose of this knowledge graph is that it should help robots to actually get access to knowledge, right? And if you go a little bit down, yes, so here. So here you have, I want the robot to execute a task. You can basically kind of look at different kinds of cutting actions like cubing or something like that, or slicing. Slicing is fine too. And you select something like a banana. And then you query the knowledge graph in order to see whether you can get some guess on what could be a robot control program, kind of, or some pieces of information a robot would need in order to execute this task, right? So this is also a piece of research that is in the start, but it gives you the idea, right? So again, we would hope that when we are having these systems, we could get actually in the knowledge graph or semantic web community and say, do you want to actually learn knowledge graphs that are actionable on robots, right? And the reason they must be very interested in doing that is, if you look in knowledge representation, you kind of have a lot of knowledge about the things that are written in recipes, but you don't have common sense, and you don't have kind of the kinds of things written in them that every human knows, right? But if we are taking those and we basically run them in simulation in our experimental environments, right? And we take the log data of these experiments, then the common sense has to be in the experiment data, right? And I think we can turn that into learning kind of problems, and by this way actually go for robot agents that, that kind of act in a much more robust and kind of much more robust and reliable ways, right? And where we can simply look what the robot actually knows, right? And why it's doing something. And if we have such explicit representation, we can say, well, you should rather cut the banana 5 times than 3 times or something like that, and we have access of how to change that. Okay, so yeah, so the big idea is we would hope for the research community in robotics to actually create in a community effort a big research building that is accessible to researchers that don't have access to robots, and that also bridges between different research communities, and so that roboticists can work together with researchers in knowledge representation, reasoning, AI planning, and everything else, right? And they can actually check whether their research is actually meaningful in terms of getting robots or getting kind of models of intelligence that can successfully act in the world, right? And this is what our ultimate purpose is. Okay. Yes. Can we show the video? So we are also kind of using that that building to actually build a curriculum for cognitive robotics. So that is a textbook that we are developing, and where it's kind of also funded by the German government, and you have videos embedded in the textbook, but you also have research-oriented teaching, right? So if you kind of go from the book and you want to do an exercise, you actually kind of come into our lab, right? And you can do your exercises and understand the subject topics by running experiments, right? And you can do that in the classroom, you can do it at home, and this is a way we hopefully can also encourage students to actually go into robotics, right? In particular, also when it's kind of robotics for helping people, right? And I think it's cool to have something like that in your lectures, and you go that and you actually have a robot that is driving around and doing, kind of turning the equations that you have learned into a robot motion, and that actually works in the real world, right? It's also, if you're thinking about it, it's that whole infrastructure can be a digital innovation platform, right? It's not only for research and working together, right? But it's also about kind of customers, robot developers, kind of application developers coming together, right? So if you have a retail store, you can actually meet in the virtual research building, kind of meet a robot developer, find somebody who is doing perception, finding somebody who's kind of writing the high-level control program, and then see would that combination actually work in my retail store, right? And you could do that in a very lightweight way. And if you are investors and you are risking a lot of money, that might be actually a feasible way of getting kind of that working. Okay, can we see the video? It's on the right. So here we have an example video where we have robots. So actually that's kind of a startup Ubica. Is that working? Or no video? Ah, yeah. So it's a startup Ubica where you basically build digital twin models of retail store, and Alexis Maldonado, who is coming from here, is actually one of the founders of the companies. And you are building these digital twins. So how long should I take? 10 minutes or? No, I think it's getting heavy, or? Okay. Yeah, so that's, and you also want to have competition environments, right? So you want to have something like RoboCup at home, RoboSoccer, and if you have running it in a virtual research building, right? So you connect the students competing in RoboCup to research, but you also can outreach to a much bigger community. So we are trying to get actually specific competition environments, specific competition tasks into our infrastructure. And the whole exercise is actually building a research community. Okay, I would just take one more thing. So just because I haven't really explained how the robot control system is working. And so we are back to that solving the body motion problem, right? So the way we are actually approaching it is that we want to develop a system 2 control program, so one that is explicitly modeling the actions, the plans, and the tasks for kind of these manipulation tasks for robots. So our proposal consists of 4 components. So we always want to basically represent things explicitly and such that the structure of the representations actually match how the things work in the real world. So we have a high-level plan. It's the generalized action plan. And the generalized action plan gets specialized into a motion plan, which specifies the robot body motions. And it does so by basically using explicitly and modularly encoded knowledge and using reasoning. So let's look at the plan. So this is kind of the high-level plan. It's simplified, but it's kind of the plan that did actually the table setting, right? And it says, well, if you want to kind of fetch an object and you want to place it at some destination, the robot has to be at the location where the object that is to be picked and placed is visible and reachable for the robot, right? And then it's performing an action of the type fetching on that object. So what is happening is that we are doing a lot of hand waving, right? So that we are kind of saying, well, it's visible and reachable, but we don't say what it actually means, and also we don't say how the object is to be grasped and whether there are special care. So that's kind of the high-level plan. So because the high-level plan is so vague and kind of so ambiguous, we have to combine it with knowledge, right? And knowledge is something like cups used for table setting have to be clean and unused. Cups in the cupboards are clean. Cups have to be grasped from the outside and things like that, right? So they help the robot to do things the right way. What is important is that these knowledge pieces are general. They are all quantified, which essentially means they also apply to objects the robot doesn't know yet, right? And this is actually a way of scaling towards open environments and open tasks. And also because they are knowledge pieces. So for instance, if we have the information that clean cups are in the cupboard, we can use it for setting the table, but we can also use it for storing the cups after we unload the dishwasher, right? So it's multiple use that is important. And the other thing is that these knowledge pieces can be composed, right? So we can put the knowledge pieces together, and then we can do more powerful kind of inferences. And those knowledge pieces can be extremely powerful, right? So there can be something like, I have a knowledge piece that says, X is the best move in a Go game, right? And when I have that piece of knowledge, I can actually call AlphaGo, and they give me that good piece, right? But in that way, I can actually integrate all the deep learned machine learning systems into modular architectures. I can give semantics to them and use them. Okay, so that's that. The motion plan. So the motion plan is actually kind of, so if you look at how humans set the table, it's extremely structured, it's extremely stereotypical, right? If you do a randomized motion planning, there would be no way that we have actually motion patterns with such low entropy like that, right? And this structure of pick and place tasks is, of course, well studied in cognitive psychology, in action science, where you basically kind of model those actions into motion phases. You say what the goals are, what the parameters are, and that helps you in designing your robot control by leveraging the knowledge in cognitive psychology, right? And if you think about that, right, so if you're thinking about your robot control system and what it should do, right, so if the task request is pour the water out and you have a pot with potatoes, what it should infer is something like grasp the pot by the handle, hold the pot horizontally, tilt the pot around the axis between the handles, hold the lid while pouring, right? So, and the reason these kind of information pieces are so important, it's actually those information pieces that make your action successful, right? And the contextualization process. So that's kind of the thing that does the work. So we are getting in with a high-level action description. So that's happening for each object in the fetch and place task. So we have something like perform an action type fetch and place. The object is of the type cup. The destination is a kitchen table, right? So you're basically taking that instruction and you expand the generalized plan. You just do a macro expansion and you get that plan. And you take all the motion parameters that you have of your motion plan and extend that, right? And then what your system has to do is it has to query the motion parameters such that the action, fetch and place, kind of succeeds when performed at this pose with these action parameters. And we can show the video so you get an impression of that. Yeah, so this is kind of how it's working in these pick and place tasks. So you see how the plan code expands, how it's looking for parameters of the motion plan, the next one that it has to execute. It mentally simulates to see whether they are expected to work. And so every step in the motion plan, every parameter is actually inferred through reasoning in that paradigm. And this is actually the magic that lies behind kind of the behaviors of the robots that we have seen in the videos. Okay. Okay. Yeah, can you stop the video, please, Israel? Okay, I just go, just show the work of the great graduate student. So this is kind of the perception system that is doing the job. Can you run the video, please? So again, the challenge is, if you're doing perception, you have many perception tasks that dynamically change, right? So you have to compute a belief state, so you have to know where all the objects are. But we will later see an episode that is much more complicated, where actually the robot is seeing kind of a person sitting on the sofa. The person is pointing at an object. The robot picks up the object that the person points to. Then it's following the person. The person is pointing at a place in the shelf, and the robot is placing it at exactly that, right? And the challenge is that there are very different perception tasks that have to be dynamically changed in order to make that successful, right? Yeah, okay, that's kind of the internal operation. But this is then what's happening in a concrete task. So it's kind of reconfiguring the perception tree while it's executing, and you see it's kind of the pointing detection is inserted into the program and then run. And if we run that on the robot, it looks like that, right? The robot the person points, robot picks up, kind of then it's following, person pointing into the shelf and putting it down. Right? And it's very clear if you have perception systems for robots that that have to perform manipulation tasks like cutting a bread or buttering a piece of bread, right? So you need very sophisticated perception mechanism that you have to configure on the fly for one particular purpose and then change it, yeah. And so one last video and then I get to the conclusion slide. Yeah. That's kind of how it computes the mental model of the situation. The situation model, yeah. And yeah, can you go, kind of delete the, yeah, and okay, and this is the very last video. So this is actually how the motion control system is working, right? So, and how actually the opening of all the doors and cupboard doors is happening, how it's running on different robots. You're kind of representing the kinematics of the robot, and the control system is kind of doing that automatically. You see grasping with different kinds of hands. And yeah, so again, it's kind of the generality of control is that matters, right? So if you have actually a robotic transformer, so GPT-like system, right, that might suggest you a motion of your hand, but you cannot tell the system that you need a collision-free path, that you want to have an optimized motion or anything else, right? So if you want to do that, you actually have to have much more sophisticated systems and understand how they kind of can be composed out of the parts. And yeah, and we are also working with Federico on these parts, and Federico has helped us a lot in those things, yeah. Okay, and you see all kinds of different things, right? So like boring, cutting, and that we are kind of grasping different objects with different strategies. Okay, so conclusion. So I think yeah, so my first conclusion is that it's very important for our research community to take the full problem, right? And this is, we need to develop robots that are successfully acting in the physical world, and this is a huge challenge, right? We are nowhere close to that, and deep learning bring us a bit in that way, but it's actually one component of the system that we need, and it's actually the one that in terms of computational mechanism is very benign. So it's a kind of a single technology, that kind of scope. If we want to have the system too, we know from cognitive psychology there are very specific cognitive capabilities, and they are extremely sophisticated. They are orchestrated by our brain to actually work together in a very synergistic way, and we know hardly anything about that. It's kind of a largely uncharted problem. The second message I wanted to get across is, if we really want to take that research task seriously, right, I think we have to do open research, right? So that there's no way that we can build kind of computational theories, computation models of such sophistication kind of individually in separated research groups, right? If we don't get our act together and actually work together, I don't think we will make the progress that we need to do fast enough, right? And the third thing is, I think, kind of the context also kind of provides a very nice context for us to work together, and I would really like to appreciate, I would really appreciate if we would find ways of actually kind of having cooperations that are fruitful for both sides. Thanks a lot.
Thank you, Michael, for such an insightful presentation. And it's always amazing, and it's full of great results. And it shows a lot of the work that he has been doing, and the great group that you have also. Thank you.
Yeah, I think it's always the team that counts, right? So I think, and then I think it's, as I said in the very beginning, right? It's without getting the right people into the team, nothing of that can happen, right? And yeah, we found some very cool ones, right?
Thank you, Michelle. Yeah. So we are open for questions. If anybody in the public wants to make any questions. Francisco?
Thank you. In the mechanical engineering area, is there any kind of limitation? Is there a big limitation in the mechanical possibilities of the robots, so that the programs can function reliably?
There is a mechanical limitation, right?
What?
A mechanical limitation,
yes,
on the robots that will make the programs not work correctly.
Oh yeah, sure. Yeah. I think it's it's a path we have to push, right? It's also the case. You don't want to make your programs overly general, right? So if they are overly general, then they become paranoid, right? So they act as everything could go wrong, and everything has to be reasoned about. So there's a trade-off that we need to understand, and that helps us to design these generalized plans. And I think that kind of is strongly connected to the way you design your robots, and and then whatever you can build in lower levels, right? So like the motion control that we have, but also the perception but also the mechanics. It helps the system, right? And the tasks are so ambitious and so hard that we actually need all the help we can get there to make these kinds of things feasible. Yeah.
So there must be a baseline of joint complexity, so the robots can function properly.
I think that's well, I think that's kind of another open research issue to actually understand how we have to evaluate and understand these systems, right? And so I mean, at the moment you see in deep learning these huge benchmark tests, right? And they are just kind of, I'm 1% better, right? But I think in these things, it's actually the question of what can one robot better than another one, and can we actually transfer that, and do we understand the design trade-offs? that requires a lot of work in how we experimentally work with these systems and also, so if you look at cognitive systems, right? So I think instead of benchmarks, we need much more something like what you do when you write the kind of the exams for your students, right? So you kind of have some questions where you design the questions for specific purposes, right? So some test the knowledge, some test the understanding, some test whether you're able to apply that. And I think, again, we need to work on those kinds of things and experimental research and how to do that right, in particular in ways that advance the field is a very important thing that researchers don't look seriously enough in, yeah.
Thank you.
Hi, Michael. Thank you for your presentation. How many questions am I allowed to make?
Well, try one first. You can do more.
Okay. Having into consideration the environments, the virtual environments that you showed us, do you think is it still necessary for universities and research centers to acquire and build physical robots and environments?
Yeah, I think it's part of the thing, right? So that you want a large variation of environments, and I think again, so there are some cool steps into the direction. Again, I think it's a question of understanding why systems fail and succeed, right? And you want to have and you want to have context-specific models of success and failure. And part of the context is the environment, right? And what actually the environment characteristics is that is critical, right? And for that we have to work on all parts, yeah.
Okay, thank you. And the second is, how should we, as, let's say, less developed countries, promote the investments in research, not just in the robotics area in general, having into consideration that sometimes politics, let's say it, don't think it's important enough to invest in research for the country development. How should we, or in your opinion, how should you promote it here?
Yeah, I think that kind of the virtual research buildings, if we do them right, would be an important step in the right direction, right? So because you also see in the high-tech countries that talents are missing. And I think there are in many places very cool talents, but I think it's also giving talents the opportunity is part of the story, right? And if we can help that, that would be very cool. And we have to see whether all of that can actually succeed. But I think this would be kind of comparatively a much more low-cost way of doing that, right? And yeah.
Okay, thank you very much.
Hi. Hi. Is there any, along the lines of open research, of acceleration of research through open collaboration, is there any project or related to networking the robots that are deployed out in the open? For instance, letting them share their knowledge about the physical world, about what their actual experience of the physical world, so that they can, not only what we humans can teach them about the world, but also what they themselves can experience, and for instance, density of fluids or textures of any other features.
Yeah, so I haven't talked about that, but I think if you're advocating open research, there are a lot of ethical aspects, dual use aspects, and geopolitical concerns, right? And yeah, you have to find the right kind of way. You can't deal with it, right? So that's kind of inherent in the system. But I think you have to make people aware. You kind of have to, so for instance, in our case, so we have researchers who look into these aspects as research topics. We also want to kind of apply the values of the European community and the way they are kind of implementing them. But that's certainly not enough what we have to do, right? And that's kind of a very important topic, and yeah, you have to be very concerned about that if you're advocating open research. Yeah.
Okay, thank you.
Here. Oh, okay.
Thanks for the presentation. It's a simple question. Is what language do you use for program the robots? But is in the physical robot, not in the metaverse or the environment. I saw that you have a Python library, PyGisker, but in the physical robot, what language used for program? C or C++ or Python is the king of the mountain? This is a question.
Yeah, you're using different languages because you kind of have different computation tasks too. I mean, Python is certainly preferred if you want to get a big community and making things easier accessible and starting them up quickly. So I mean, in the high-level program, so after, I guess, 25 years, so the doctoral students convinced me that we are finally not using Lisp anymore, which is kind of a very old language, but that we are going for Python just to make it easier for people to actually do that. And yeah, but in general, I think it's a very complex system with very different tasks. The better you design your system so it matches the problem you want to solve, and the better the programming language is that makes what you need explicit and tunable, right, the better it is, right? So it's a pragmatic choice, yeah, I think.
Yeah.
Hello, I noticed you have very many videos, very successful attempts with the robots. So I was wondering what the percentage is of actual successful attempts versus failed attempts with the robots you have developed, and if, how quickly you get to increase this percentage.
So in terms of the program controlling the robot and not the programmers getting to program the robot successfully, right? The first one is the one, right?
Oh yes, I'm sorry, I meant...
So the thing is, when we program the robots to be successful, right, so you can take that specific program, right, and kind of make it robust, or you can think about how to actually teach kind of researchers to write such programs, which is kind of still one level more complicated, right? So when we go for robust control system, it's actually kind of a very tedious job. It's kind of heavy software design, and you kind of have to. But if the designs are good, then you have a better chance of pushing it, right? So if I mean, there are a lot of techniques in computer science that help you to write kind of good code, in particular for systems that fail often, that are concurrent, that are reactive, right? And you want to basically use those concepts to get better design of the system, and this pays off. But still, I would guess that at least 75–80% of the code is failure detection, failure analysis, and recovering the right way from it. So, and the same is for, we know that from humans too, right? So that humans, when they do manipulation actions, they fail extremely frequently, but their failure recovery is very deep in their control system. And I think that's the nature of the problem, yeah.
Thank you.
Hello, thank you for being here. I have a question regarding transformers, the transformer architecture. You mentioned that these types of systems, like ChatGPT, the knowledge they have is encoded in the weights, and that is not possible right now to make that knowledge explicit in a knowledge base. So my question would be if you think that that's an intrinsic limitation of the technology, that composition with other technologies might be needed to make it so, or do you think that there's a way for transformers to really get at the task and solve the problems in more explicit ways?
I mean, this is my complete personal opinion, and I might not be right? But I mean, if you look at introduction in computer science according to one of the seminal textbooks, right? The thing they write is, it's kind of one of the most important lessons for a computer scientist, that a program is not just a specification of the computation that is executed, but it's actually a way of communicating how the problem is solved, right? And in computer science, you're simply developing control and data abstractions in order to support that from the first thing, right? Whether, how far you can push in, I think that it's very clear that people in deep learning push into those directions. The question is how far one can get, right? And you also have these asymptotic performance, right? So that, the work you have to spend in order to get a small delta becomes more and more, and that might be a kind of an indication that the framework is not sufficient for all what you want to do, right? Yeah.
Thanks.
Yeah. Thank you very much for your presentation. It was very interesting. So I am interested in, let's say, the physics of objects and how objects that are changing because of actions could work. So for example, if you are talking about pancakes, they start like a pancake mix that is liquid and has some physical properties, but then when they become a pancake, they're a solid and you have to treat them differently, right? Or there are many examples for when you are cooking. For example, you have a lot of ingredients and then they become a soup. So the physical properties are changing as you are performing the actions. So what do you think are the main challenges for robots to be able to work with these transforming objects, and or are we already there and we are already able to do these tasks?
No, I think this is kind of one of the greatest challenges, right? So if you think of a task like cutting, what you mean is cutting any object with any tool for any purpose under any constraints, right? And I think it's just the nature and again, I think it's kind of aspects of the problem that are very uncharted and that are open challenges, and it needs researchers to look into those aspects, and they are extremely important, yeah. I mean, the other, so there's also, I mean, when I was in graduate school, people were saying you can only learn something that you understood, right? So, and I think this is kind of now not the kind of the view of the main bunch of people, but I think it's, I still buy that, right? So I think you have to learn how to program and how to deal with these issues in specific cases, right? So because you need to get an understanding of the problem, right? So if you know the solution before you have understood the problem, you know that you are on the wrong way, right? And yeah.
Very much.
There at the end.
Yeah. Yeah, I had another question talking more about this topic of open research. I was wondering if there are any computing constraints on running this simulation framework that you provide, and if there are like future computing constraints, if we're going to need like high performance computing in order to further improve these simulation engines in the future.
Yeah, we have to see. So I think it's, so the way, I mean, the way I look at all these activities, it's like a betting system, right? So you have a vision, you have some reward, you can put efforts on that. Whether that actually pays off or not is questionable, and you have to kind of take your bets, right? So for me, actually, open research and the positive impact that it can have is simply a bet that I want to take, right? And getting companies, kind of getting the software industrial strength and getting it used by companies are necessary steps to being successful, right? And yeah. So we are talking to companies, but whether that will be successful or not is out of our scope, right? So we hope, but yeah.
Thank you.
At the end.
Hi. Well, first of all, thank you for the presentation. One aspect I was thinking about was the knowledge-based perception approach. My question is, it seems like you need to design the queries, the motions, the sequence of tasks beforehand. Do you foresee any future improvements where the system can learn itself, like new concepts and new sequences by itself?
Yeah. So I think, so the question is, again, in a research area that is so ambitious, you want to identify sweet spots, right? And I think sweet spots is something like the pick and place tasks that we believe now have a very common stereotypical structure, and you can solve a lot of tasks with that, right? But we are also, in particular, when we learn manipulation plans from the web, we are also now looking into what are the atomic motions Can we actually represent them in the way they can be dynamically combined, which would basically mean that we can create a much richer space of behaviors. And yeah, this is just some, again, I think it's the lesson for me is everything is an ensemble of methods, right? And you want the methods to be not overly general, because you have to pay for the overly generality with infeasibility, right? So that you kind of cannot write the programs for solving the problems in their whole generality, yeah.
Okay, I do have a follow-up question, if that's okay.
Yeah.
No problem.
Okay, so curious, reinforcement learning, would that be something that you would consider for this particular context?
Yeah, again, reinforcement learning is part of the game. Again, the strength is its simplicity, and you have that very general optimization principle in there, but you don't have kind of the control abstractions and kind of more specific information. So we have a doctoral student who is pushing reinforcement learning to combine it with knowledge-enabled techniques, and also with joint probability distributions of experience to actually explore just much faster. And I think we have to do much more in reinforcement learning. But yeah, I think, again, at the moment, the big game that I see most of the people doing is killing every problem with data, right? And we had that before, right? So if you have a tracking system and your tracking system has an extremely high frequency, you don't need to do prediction, right? And prediction is a more complicated action. And I think it's, but I think I think that basically throwing all the computational power at the problems and try to do it with methods that are comparatively dumb is not the way that we will be successful, yeah.
Thank you.
Sorry, I would like to ask another question, if that's right.
Sure.
As you said, and as I understood, you said that this robot cannot be overly general because it simply couldn't predict everything that's going to happen. So would you be open to ask, for example, the human user to maybe fulfill some requirements for the robot to work properly? Like, for example, having a specific set of dishes for the robot to recognize, or maybe these dishes need to be like, for example, a non-stick pen needs its non-stickiness to still be working, something like that.
Yeah. Definitely. So I mean, we know kind of from the way how we teach our kids, right? So that actually giving instructions, advice, explaining concepts is a great promoter for learning in a much more robust and faster way. So getting the humans into the game is a necessary step, right? So the thing is, if you have a research group, you have to make your choices, which of the topics you are actually tackling with the doctoral student, right? And that, yeah, so you cannot basically tackle all the problems that should be tackled, yeah.
Hey, well, first of all, thanks for the talk. And I have a very small question. It's regarding the curse of dimensionality in these like real environments with real tools that the road has to handle. How do you cut off some features, or how do you make it work in?
Can you say a bit louder?
Sorry. Oh. Okay. First of all, thanks for the talk. And my question is regarding the curse of dimensionality. How do you handle this in these like real life environments with, I don't know, a kitchen with a real knife, real dishes, whatever? How do you prune those features so the algorithm can perform in like a decent time?
I think we are not kind of dealing with those aspects in a principled way, right? Again, I mean, we are thinking more in terms of doctoral student dissertations, right? So it's more like having a scientific hypothesis and kind of validating that. And I think we see from autonomous vehicles kind of how big the step is from kind of individual solutions to subtopics to something that is very principled solutions and understood solutions here. So I think if you look at the videos and you extrapolate, we can do everything. So that's kind of a misconception, and that it's also something that I don't want to communicate, right? In most cases, it's actually that is what's working. But I think, as I said, so I think, I mean, research goes in phases, and the first phases are experiments with some new concepts, right? And then it's about forming theories and pushing them and getting for more principled. And I think at the moment, we don't have enough knowledge, right, and to actually go for the principled things.
Okay, thank you.
Okay, hi again. You made reference at the end of your talk to our huge ignorance regarding the inner workings of the brain and the body. So I have basically two questions. The first one is, how contingent is AI and robotics research on further developments in cognitive and neuroscience, and how do you handle that in a pragmatic way at your laboratory? And yeah, how do you handle the interdisciplinary requirements of the problem that you are solving?
Yeah, so I'm cheating, right? So I'm cheating in the way that we are only going for physical manipulation actions, which are kind of body motions and their physical effects. So there are kind of lots of things in terms of social interaction where kind of you don't know exactly what the actions are, you don't know what the effects are, and the effects might be very delayed, and so yeah. But in that aspect, I think it can help to understand what common sense is and what you need to do a physical action successfully. So it might help to get a better understanding, or at least a perspective on diseases like dementia or Alzheimer, to better understand what is really missing, right? And yeah, we have to see.
Michelle, hi. I'm just trying to make sense of some ideas I got in the last weeks that still are running on my head. You mentioned that the relationship between cognition and the interaction of the robots in the world that needs to be successful in order to create systems that go and push beyond. Do you still think that it's valuable to learn from human motions, movements, in order to use that example, or even not only humans, other mammals or any other animals, in order to learn some of the patterns, the motions, in order to interact with this world? What do you think?
I've not shown that video, but I think it's actually understanding human motions, right? There's also a field called action science, which is kind of pushing that, and it's always, you have research on the analytical side, and you have research on the generative or creative side, and both should help each other, right? And I think having very good explanation models of human motion and how they do things would greatly help, yeah.
I have heard, Federico, that have heard from someone else that if a human can perform it, maybe a robot will. Will that be possible to say a
That's
yes?
something that Gordon Cheng did.
If a human can do it, a robot can do it.
That a human can do it. If I can put a T-shirt on top, the robot can do it also.
I mean, I'm not sure whether it's a belief or whether it's actually a challenge, right? And I think it's probably humans, robots can do many things that humans cannot do, right? So that's kind of the easy part. But I think in particular in terms of cognitive capabilities, I think we are very, very far ahead of getting anything that is remotely comparable, yeah.
Thank you, everybody. Thanks for the presentation, Michael. It was great, and all the answers for the questions that we had. And we are really happy to have you here in Costa Rica for the first time. Hopefully more times even. We will try. Thank you to everybody for coming to this event today. And this is going to be available in one of the social networks that we have. We will send the details together with the previous announcement, so you can look for the video in case you have any questions or, well, you want to clarify more. So thank you, Michael.
Cool. Thanks a lot. Yeah, thanks. Great questions, and it was fun, yeah.
Thank you.
Bueno, de nuevo, muchísimas gracias por estar por acá, los que están aquí aún presentes, los que tuvieron que irse a clases y verán el video posteriormente. Gracias a quienes nos acompañaron en redes sociales. Editaremos también el video para, como dice Federico, tenerlo disponible a posteriori. También Michael va a andar en estos días con nosotros, así si alguien tiene alguna pregunta nos puede contactar. Puede ser a mi Telegram, @Feciles, y ahí buscamos alguna pregunta, tratar de traducírsela y respondérsela a través de lo que diga Michael. Muchas gracias a todos y que tengan una excelente tarde. Gracias.